Good morning, physical geology students. Today we're going to be focusing on faults and earthquakes. So some of the objectives today are going to be what is a fault, what is an earthquake, how seismographs work, types of seismic waves we're going to talk about, locating an earthquake, and we'll look at earthquake hazards and the Earth's interior. And here's just a photo showing in Kobe, Japan, 1995. This is the aftermath of one of the earthquakes that occurred there. So I want to recall, I talked maybe briefly about this in the past about different types of faults. Basically, what is a fault? And essentially, they are fractures along which movement has occurred. So faults are classified by the type of movement they have. So there's two types. There's a dip slip, which is basically faults which have movement that is mainly parallel to the dip of the fault plane. And then there's strike slip faults, and these are faults which have mainly horizontal movement. In the example, this would be the famous San Andreas fault system in California. Joints, I think I briefly talked about what joints are, and joints are essentially a fracture, but there's no movement has occurred along a joint. So there's no evidence of that. So types of faults, here's kind of from your book, they show some of these block models. So here's the famous strike slip fault, or also they call it a shear, or a shear fault. And this is the one that takes place in California. So you're going to have two different blocks, and these blocks move in opposite directions. So this block is going to move in this direction relative to this direction here. Here's your normal fault, and this develops in tension. So here, for an example, you're going to be pulling apart these blocks, and what's going to happen is this block is going to want to move down this direction relative to this block. Typically, the miners would call this the hanging wall and then the foot wall. And if you were to put a little miner in here, and his head would be in this kind of part of this block, and his feet would dangle down on this block. So they would talk about that, basically that the hanging moved down relative to the foot wall, or the foot wall moved down relative to the hanging wall. So they use that kind of as a guide. Then lastly, there's this reverse fault. This is called where compression happens. So you're actually squeezing these rocks, and then these rocks are moving up. So if you were to put this little stick figure in here, in this situation, the hanging wall would move up relative to the foot wall here. So it's being squeezed. So those are the three types of faults that occur during faulting. During some tectonic event, the rocks are either being pulled apart or squeezed, depending on the geologic setting. So what type of fault would this? This would be kind of a dip slip fault in Oregon, and you can see the different layers of rock here. It looks like that this is kind of a soil profile, but these different layers are showing you a dip slip fault. So here's the fault plane, which is cut right through here. Let's go back and look at the dip slip fault. Here. So the dip slip faults which have movement that is mainly parallel to the fault plane. So if we go back here, so here is the fault plane, and movement has occurred along here, along this fault plane. So you can kind of, these layers, you should be able to kind of reconstruct, or you can actually put these layers together, join these layers together to kind of retrace the movement of the fault. So it looks like these layers it looks like this layer has moved down relative to these upper layers here. So then there's also these types of features that you get in the out west in Nevada and in California. You get these Horst and Graben type features, and these result from horizontal extension in the crust. So here, if you pull apart the crust here, what's going to happen is these blocks, this block will drop down, and they call this a Graben. These are both German. These are German names, Horst and Graben. So this is going to drop down, and then this Horst is going to come up, and these Horsts are usually mountain ranges that occur in this Horst type system. So this is a Horst and Graben. And here's some more. This is types. They're showing you a block diagram of some normal faults, and it looks like this crust is in tension, and you're getting these kind of faults like here that are curved here, and then these would be your Horsts, and these little areas would be your Grabens here. And here's kind of just showing you an example out in Nevada or California. You get so here are going to be, these are the Horsts, and then in here is probably the Graben. So here's just another model kind of showing you Horsts and Grabens in California. So here they're showing you, here are the Sierra Nevada mountains, and you have Owens Valley, which would be a Graben, and then you have here is the Inyo Mountains here, and then you have here this Deep Springs Valley where you have a lot of the sediments that accumulate would be a Graben, and here is showing you kind of the underlying bedrock here. So here's going into detail on more on what thrust faulting development looks like, and here up at diagram A, it's showing you basically the dotted line is the thrust fault, and typically you have Cretaceous rocks here and you have Precambrian rocks. So if you know the relative age of the ages of these geologic ages, the Precambrian obviously is a lot older than your Cretaceous rock. So typically in a thrust fault, you're going to have your older rocks are going to be thrust over your younger rocks. And here is showing at B, it's showing here's stress. So the rocks are being squeezed and thrust over the Cretaceous rocks. Here it's kind of showing you again the later development at C. It's being thrust over here. And then at D, it's showing in the end that we have these Precambrian rocks that have been thrust over the Cretaceous rocks here at Glacier National Park. So here's kind of an oblique view of the San Andreas Fault. So this little line here that is coming through and cutting across this valley, this is the San Andreas Fault. So movement, if you look closely enough, you should be able to, it looks like movement is this way, and then this way movement would be. So they can actually measure this very precisely with GPS and calculate the movement, how many centimeters per year that the San Andreas the fault is moving. So this is very interesting. We can also use different types of fences or a concrete barrier. And this here is showing, again, you can see a little grass kind of squeezing through these cracks, and this is evidence of creeping, soil creep, as well as faulting. We can actually use these objects to calculate measurements in drain faulting. So this is just showing you here the kind of the fault and locked segments, and then creeping segments. So they can calculate based on different objects that they can use. But you can see here, notice the faulting is kind of it's not one single solid fault. You've got these little branches that come off. Here's the Banning Fault, and then you've got the Garlock Fault. But you've got multiple branches off the San Andreas Fault that kind of migrate into different, different cities. Here's San Francisco, but here, see how the branches come off? You've got the Hayward Fault and the Culveris Fault. So, in order what causes an earthquake, and essentially earthquakes are driven by these faults that we talked about. There's regional shear fault. There's also the regional tension that we get. This is normal faulting, and then we have thrust faulting, which was regional compression. So these actually, the energy that is released or from faulting is what creates these earthquake waves to propagate through the crust. And we're going to talk about primary waves and shear waves. So this is the elastic rebound theory, and this is like it's just showing you a kind of a hypothetical fault plane here that runs through the crust here, and what happens is the stress actually builds up inside the rocks, and that strain that builds up on either side of the fault, it's released, and once that's released, the strain is released, you get an earthquake. And we'll talk about the different types of waves that result from this. So I'm going to stop here, and then we'll start up, and we'll talk more about the different types of earthquake waves that propagate through the Earth's crust. Thanks.